All right, as promised, here's the video where I will go over the proof and we'll look at an example for the 3.6 types problems. And I'll circle back and revisit the test review, which I think was cut off. So as we said, we have, again, the complementary solution that we call the homogeneous solution, which is right here at the top. Then we need to reorganize our equation so that we have the lead coefficient of 1. And we also said that we have this assumption here that the particular solution would have the form of some function u1 times y1 and some function u2 times y2. So here again, we have two unknowns that we're trying to solve. Our goal is to find u1 and u2. So the idea is we are going to plug our solution into the differential equation. So here we're taking the first derivative using the product rule. Notice that the in-between part, u1 prime times u1 plus u2 prime times u2, we're going to make the assumption that that satisfies the condition that sum, that part is 0. He's saying that in this case, we're just making that assumption. We're not proving it, but you're going to see that that assumption does work out. So our strategy for the proof is let's make an assumption that makes our life easier. Hopefully we can prove as we go through the proof that that assumption makes sense. So given that assumption, we simplify our first derivative of the particular solution to be u1 y1 prime plus u2 y2 prime. Then again, using the product rule, we get the second derivative as you can see. And then we're plugging it into our differential equation. Again, this is a proof in general because this method does work even if we don't have constant coefficients. All of the problems we're going to encounter will have constant coefficients. So you can again see we're just substituting p of t times y double prime plus q of t times y prime with our assumption that that part of y prime would be 0 and r of t times y equals some g of t. Then we do some algebra combining like terms to get this next line right here where you can see the highlight, p of t times the u1, y1 both prime, etc. And now we notice, again, both little y1 and little y2, remember our solutions to that number 2 is the homogeneous equation. So therefore, the second and third terms will end up being 0, meaning anytime I have a constant times y1 and or a constant times y2, when I've plugged that into my differential equation, since that's a solution to the homogeneous equation, that means that when I evaluate my differential equation with those solutions, the answer should equal 0. So therefore, I can zero out the parts that are 0, and it simplifies to be this p of t, u1, y1 prime, u2 prime, y2 prime, plus u1 times 0, because that was a solution to the homogeneous equation, u2 times 0, because that part is a solution to the homogeneous equation, equals g of t. So then we get u1 prime y1 prime plus u2 prime y2 prime equals g of t over p of t. We've got two unknowns. We're going to need a couple equations, so we're almost done. So we're going to go back and make another assumption. And again, we're hoping our assumptions work out in the course of our proof, that we can validate they were reasonable assumptions. So the last equation is actually the one that we want. However, in order to make things simpler, we're going to start with assuming that lead coefficient is 1. So in other words, we're rearranging everything, which again, we can always do by dividing through by p of t. So he started out with letting there be some p of t being whatever, and now we're going to assume it's 1, which is an assumption we can always make work because I can always rearrange the equation so that that is in fact the case. So with that assumption, I can now simplify things to have this u1 prime times y1 plus u2 prime times y2 equals 0. If you recall, that was the assumption we said we made along the way to hope things worked out. So that needs to be true for our process to be true. And then we have u1 after solving and plugging everything in and simplifying, u1 prime y1 prime plus u2 prime y2 prime equals g of t. Because again, we are assuming p of t is 1. Which is a reasonable assumption because if it was not 1 to begin with, I can always divide through by p of t. So now I have a system of two unknowns with two equations, so we can solve it. Again, it's a system of differential equations, but hopefully we can solve it. Our goal is to find u1 and u2. So here we're just going to do an algebra system of substitution. We solved the first equation for u1 prime. And then into the second equation, wherever I saw u1 prime, I replaced it with this negative u2 prime y2 over y1. Again, this is not pretty, but I'm just doing some algebra and rearranging. And then I get a formula for u2 prime in terms of y1, y2, y1 prime, y2 prime, and g of t, which are all things I know. G of t is that right-hand side of the equation, which is given. Y1 and Y2 are solutions to the homogeneous equation, a fundamental set, which I know how to find. And then, of course, once I have Y1 and Y2, I can find their derivatives. And when we look at this, in this part we did talk about in the previous video, we recognize that denominator as being the Wronskian. And since we are assuming that Y1 and Y2 we are using is a fundamental set, we know that the Wronskian would be non-zero. And then, of course, I want u1 and u2, not their derivatives. So the inverse of the derivative is the integral. So integrating both of those, here we are at the formula that was presented in the other video. And again, the link to these notes, I think I sent both on, they're both on OneNote on Canvas and I believe in the announcements for Canvas. You can go back and read these in more detail if you would like to. So, and again, these formulas you do need to know, but you don't have to be able to derive them. So let's look at a quick example together. So here's an example in example 1, and this is very similar to some of your homework. So notice our guess and check method won't work here because our right-hand side is not a nice function, it's tangent. So in this case, we would first need to divide through by 2 to put it in that standard form where the lead coefficient is 1. Which would give us y double prime plus 9y equals 3, tangent of 3t. So the g of t is going to be 3 tangent of 3t. To find y1 and y2, I would need to solve the homogeneous equation. So going through to do that, my homogeneous equation would be r squared plus 9r equals 0. So I can factor out, so I can solve that. I'm going to get imaginary numbers. I'm going to leave it to you as well to verify that. You should pause the video and make sure you know how to do that. Again, the setup was r squared plus, actually r squared plus 9. Sorry, not 9r because that's just y. So r squared plus 9 equals 0, which would give us r is plus or minus 3i. So then using our Euler's method and our theorems, we end up with our two fundamental solutions being the cosine of 3t and the sine of 3t. So there's my complementary solution. Again, it doesn't matter which one you called y1 or y2 as long as you're then consistent. So we're going to call y1 cosine of 3t, y2 sine of 3t. I need the Wronskian not to verify this is a fundamental solution. I know that that process always gives me a fundamental set, but the Wronskian is part of the formula for finding the particular solution. So now I have everything I need. So now we're just plugging it into the formula. So that particular solution is the opposite of y1 times the integral of y2, which is sine of 3t times g of t, which is 3 times the tangent of 3t. So that 3 in the front is because g of t is 3 times the tangent of 3t. They just moved the 3 into the front. So y2 sine of 3t, g of t is 3 times the tangent of 3t over the Wronskian, which we computed to be 3. And then plus y2, which is the sine of 3t, times the integral of y1, which is cosine of 3t, times g of t over the Wronskian. Notice the patterns here. One of these definitely has to be a negative. One of them is positive. And whatever function you have outside the integral, it is the other fundamental solution that's in the numerator inside the integral. Then the rest is the same, multiplied by g of t divided by the Wronskian. And then you just do math. So we simplify the integral in this case, and sometimes, again, remember you can have technology to help you with the integration as well as a table of integrals. Certainly basic integrals you should be able to do, so you want to use kind of common sense as to what's the most efficient method. So here we're first simplifying, right? The 3's cancel out. Tangent is sine over cosine, which is where we got sine squared of 3t over cosine of 3t. And then on the second one here, tangent is sine over cosine, so the cosines cancel out. The 3's cancel out, we're left with sine. Again, just kind of moving down to do our integration. On the first one, we decided to rewrite sine squared in terms of cosine squared since I've got cosines. Then I can break the integral up. 1 over cosine is secant. Cosine squared over cosine is cosine. The second integral is already simplified. This one, if you don't have to memorize the antiderivative of secant, I don't expect anyone to know that, but you can always, it should be on the table. You can also use technology. So the antiderivative of secant is this ln of secant plus tangent. And then we have that chain, the u sub basically inside with the 3. That's where we have the divided by 3 over here. And the antiderivative, and then they already took the sign because the antiderivative of cosine is sine, right? When I distributed this cosine squared divided by cosine is cosine. Antiderivative of negative cosine is negative sine. And then here the antiderivative of sine is negative cosine. Simplifying everything, we get this beautiful expression. So putting it all together, our general solution is the complementary solution, which we found to be C1 cosine of 3t plus C2 sine of 3t, and then plus our particular solution, which using our new formula, we found to be negative cosine of 3t over 3 times the ln of secant of 3t plus tangent of 3t. And then all of them, again, the integration and the computation gets different, but it's all the same strategy. This is also a great resource. Notice there's a lot of examples where you can click show solution. And then if you go to the top, I believe there's also a link for some practice problems as well. Not to mention, of course, the homework. And in the last 4 minutes that I have on this video, or possibly less, let's revisit again our test review, which remember is the last page under the chapter 3-4 tab in your OneNote. I think I went by this very fast in the first video. So basically chapter 3 and chapter 4, emphasis on chapter 3. Chapter 4 is the same stuff with the higher orders. Most of the time was spent on homogeneous equations. All the time we have constant coefficients. So your first step is always going to be to find that characteristic equation or polynomial. And then you end up with essentially a few different options. Option 1 is that you get distinct roots. And then here I have kind of a general summary of what happens. Here's what our general solution looks like. If we get the repeated roots, then we multiply by a t or a higher power of t, depending how many times it repeats. And if we have complex roots, I jumped right from what r is to the final solution. But to do that again, we used our method of using e to the rt, algebra to break up the e, Euler's formula to rewrite our e to the it as cosine and sine, and our theorem that said if a linear combination of sine and cosine is a solution, so are sine and cosine by themselves. And I think here I am missing my e to the lambda t, so I will add that there. And then for nth order homogeneous equations, the same exact thing, except that we're going to get, higher degree polynomials. So solving for r might take a little bit more algebra pre-calc work. You can use technology, solving by graphing. You can use log synthetic division. If you have a complex root where the degree is higher than 2, then you would use de Moivre's theorem. On the test, you should expect all of the algebra solving to be pretty straightforward because I really want to see if you understand the differential equations. Then the other comment was, of course, all of our fundamental solutions need to be linearly independent. The way to check that is with the Wronskian. I did not put any of these longer, like option 2, linearly independent methods on there. Anything you need to check would be a maximum 2x2 determinant, which we should all know how to do by hand as well. Then the second kind of equations that we started looking at were the non-homogeneous equations. We still stuck with constant coefficients. That's what we've been doing this week. So we have 2 options. One of them is the guess and check or undetermined coefficients. And option 2 is the variation of parameters, which is what the previous videos have been about. In both cases, for a non-homogeneous equation, your solution is going to be the complementary solution to the homogeneous equation, plus the particular solution. And your options to find the particular solution are the guess and check method. And this is really only good for exponential functions, sine, cosine, or polynomials. Or you can use this variation of parameters where we've only done this for second order equations, by the way. And then we have that formula that helps us find what the particular solution is. And that is pretty much the entire test. Tests in general are challenging because it's a lot of different topics at once. But I think you'll find the individual problems on the test are like the easier problems from the homework.